Hello everyone, good morning. Previously we have talked about what is the introduction about the wave function. Today I will briefly discuss about what is the double slit experiment, which is tested using the electrons, and this is have been firstly conducted by the scientist Thomas Young. So mainly, in just a brief thing, this experiment used to prove that the nature of the electron as the wave nature, and it's not a particle nature, or to prove the nature of the electron as a particle wave nature. Double slit has been seated into the board within the wavelength order. It is placed into the projection screen, and the electrons were targeted to pass through those slits to make a glow through the collision between the electron and the projected fluorescent screen. Then, if the electron act as wave, the diffraction pattern on the following screen would be expected. So we expect like diffraction pattern and kind of wave pattern after the collision happened. So this is the electron beam gun and the source of electron, and this is the slit where the electrons will be passed through, and finally this is the projected screen or fluorescent screen where is the glow will happen after the electron pass from. And the fluorescent screen used to visualize the pattern through the strike between electrons and the screen diffraction location. From this experiment, we will have different kind of fringes. We will have constructive interferes of the wave leads to bright fringes, and we will have destructive interferes leads to darker fringes. So this is in this one. So this is the darker. I mean the white one will present the darker, which is the destructive, and the bright one, which is in this figure, is the blue one, is the bright fringes. Maybe the more collision of electron, maybe more density of electrons have been projected in these regions. Higher intensity, from the same figure we will have higher intensity, which is more bright near to the center, and as we get broader from the center, the bright and the intensity decreases. In Thomas Young's experiment, light formed interfere pattern that is visible to the eye, and electron force simple pattern with light. So this is just what we are mentioning. So this is what will happen if we are projecting several electrons at once. But what will happen if we only let the experiment or the slit to pass one electron each specific time? So this is three figures. This is the experiment set, and if we let the electron, to be passed through this experiment, we will have random collisions points. But if we run the experiment for a very long time, finally we will have this is emerge will be happen, or converge will be happen. Finally, this is kind of pattern will finally formed after a lot of single electrons each time has been projected and targeted the region. So in this we will have like blank region or empty region, and we will have maybe red regions or dotted region. So The empty region represents the dark fringes, or where the destructive interference happened, and the region where few electrons strike those region. In this blank or empty or dark region, there were few electrons collided into this region. So we have electron density is the least here, and it's almost zero in some region like home. There is empty dotted, but the dotted region, where is the more intense number of electrons were projected, imposed the most electron collision and the most intensity and higher brightness. So note, it would be impossible to predict where each individual electron would strike the screen, while instead of that predicting where it will be projected, we could predict the probability for the electron to strike a certain region of the screen. So we could predict the amount of electron will be projected in a specific area, but we cannot, or maybe it's impossible or somewhat difficult, I don't know, maybe one day we can reach this huge analysis expectation to predict where it would, a specific electron, where it would collide or cause the collision spot. So this maybe remind us of the previous class term to use the probability density, which is psi squared, such as the probability of electron inside the dark region is the smallest and almost zero, while the higher probability is in the dotted or bright region. So in the summary of this class, the most important point is once the interference of the wave occur, the diffraction pattern will occur. And since one electron is allowed to flow through one slit at a specific time, this implies the electron must travel through both openings, slit, at the same time to produce the wave interferences, and that is only occurs if the electron has the wave nature. So in other words, if the electron has particle nature, so there would be only one particle pass one single slit, one of these slits at the same time, if it's particle nature, and it will pass through this slit at the specific time. But it's impossible that if it's particle nature, that one electron to pass the same slits, both slits at the same time, at the same moment. This is impossible unless it has the wave nature, and this is what we proved, that electron has wave nature. The last line, that psi measured the displacement or the strength amplitude of those waves, and psi squared the probability density of electron. And I would like to thank for listening to my class, and wish to see you in another recording classes for the quantum mechanics introduction. Thank you.